The intention of today's video is to solidify your understanding of Rolle's theorem, mean value theorem, and your first derivative test. So first off, a review of what Rolle's theorem is. We've got if f of x is continuous on the closed interval AB, and differentiable on the open interval AB, and f of A is equal to f of B, so that's saying the y values of the endpoints are the same, then we can conclude that f prime of C is going to equal 0, given C is somewhere in the open interval AB. Okay, remember that little symbol just means contained in. C is contained in the open interval AB. So let's see if we can apply Rolle's theorem to this first one. Now, it's important that you go through and check each of your initial conditions. So let's start out with continuous. It's a polynomial, so therefore it's continuous. And for that same reason, that means it's differentiable. We now need to check and see, does f of 0 equal f of 2? Well, when you plug in 0, you get back 0. When you plug in 2, you get 2 squared minus 2 times 2. That's 4 minus 4, which is 0. So that does check out. So this now qualifies for Rolle's theorem. With Rolle's theorem, we know we'll take the derivative and set that derivative equal to 0. We'll add over a 2 and divide by 2 to get that x equals 1. Now always check, make sure it's in our interval. X equals 1 is in the interval, so therefore this is our value of C that satisfies Rolle's theorem. Let's try another one. We're working with a polynomial again, so it's continuous. For the same reason, that means it's differentiable. We need to check and see, does f of negative 3 equal f of positive 3? Well, because when you square a negative 3 and raise negative 3 to the 4th, you'll get back the same thing as when you square a positive 3 and raise a positive 3 to the 4th. They are going to be equal. So we didn't even necessarily have to find out the actual value, but we could tell they're equal just because it's an even function. So by Rolle's theorem, we now know that if we take the derivative, we should be able to set it equal to 0 to find a value of x where there's a horizontal tangent line in our interval. So our derivative will be 18x minus 4x cubed. We'll set that equal to 0. We can pull out a 2x, leaving us with 9x minus, or sorry, just 9 minus 2x squared. We'll set both parts equal to 0. On the left, we'll just get x equals 0. On the right, we'll add the 2x over, 2x squared over, giving us x squared equals 9 halves. And when we take the square root, we'll have positive and negative square root of 9 halves equal to x. Well, 9 halves is 4.5. The square root of 4.5, well, 4.5 is in between 4 and 9. Since square root of 4 is 2, and square root of 9 is 3, square root of 4.5 must be somewhere in between 2 and 3. So both plus and minus, those numbers will be in our interval, so both are acceptable. And you could neaten that radical up if you want, but you don't have to. Next example, number 3, continuous. Well, it's an absolute value that's flipped and just shifted up 1, so it is continuous. Differentiable absolute value is not differentiable at the point. So in this case, it would be when x equals 0, which is in our interval. It is not differentiable, so therefore Rolle's does not apply. Looking at number 4, we've got a polynomial, so it's continuous and differentiable. And we need to check, does f of 0 equal f of 1? Well, when you put in 0, we get back 0. When you put in 1, we get 1 plus 1, which is 2. Those are not equal, so therefore, again, we get one where Rolle's does not apply. So these last two show that it's important you have to check your initial conditions first to see if you can even do Rolle's theorem. Next, we'll review the mean value theorem. To start out, our initial conditions, same as the first two initial conditions in Rolle's. If f of x is continuous on the closed interval AB and differentiable on the open interval AB, then the thing we know is true is that our derivative at some point C should be equal to the slope between our endpoints. So that means we're doing f of b minus f of a over b minus a. And you could write that as f of a minus f of b over a minus b, as long as you're consistent with what you're doing. And just like the other one, that's assuming that c is in the open interval AB. So somewhere in between a and b, the slope of that tangent line should be equal to the slope between the two endpoints. So let's try this first example. So continuous, because it's an x cubed is also differentiable. So we know we have negative 1 as one x value. We've got 1 as one x value. Let's find the y values that go with them. Negative 1 cubed will give us negative 1 back. 1 cubed will give us positive 1 back. So let's find our slope. 1 minus a negative 1 over 1 minus a negative 1. That'll give us 2 over 2. So we'll therefore have a slope of 1. We'll take our derivative and get 3x squared. And in mean value theorem, you set your derivative equal to the slope that you found between the endpoints. Divide the 3 over, and we'll take the square root, and x will be equal to plus and minus square root of 1/3. Remember to always check, see if that is in your interval. Well, we're going from negative 1 to 1, so both the positive and the negative square roots of 1/3 will be in our interval. So that value works for both. What that's saying is at those x values, the slope of the tangent line will equal the slope of the tangent line when connecting the two endpoints. And we'll look at one more mean value example. So starting out, continuous it is because it's a polynomial, and for the same reason, it's differentiable. We're working with the x values negative 1 and 1. We need to find the y values that go with those. When we plug in negative 2, we'll get a positive 4 times 3, which is 12. We'll get a negative 12, and we'll have a minus 5, giving us back the y value of minus 5. When we plug in 1, it's a little easier. We'll just have 3 plus 6, which is 9. 9 minus 5, which is 4. Finding the slope between those endpoints, we'll have 4 minus the negative 5 over 1 minus the negative 2. That'll become 9 over 3, so we just get a slope of 3. We'll come back over here and take the derivative, which will be 6x plus 6. And again, remember when you're doing mean value theorem, you set the derivative equal to the slope between the endpoints. So we'll have 6x plus 6 is equal to 3. Subtract your 6 over, we'll get 6x is equal to negative 3. And dividing your 6 over, you get x is equal to negative 1/2. Just double check, make sure it's in your interval, and negative 1/2 is in between negative 2 and 1, meaning that this value of x is where the slope of our tangent line will be equal to the slope when you connect the two endpoints. To review our first derivative test, at a critical point, when you switch from positive to negative for the derivative, that means you went from increase to decrease, so you've got a max. If you went from negative to positive, that means you went decrease to increase, so you have a min. And if you stay the same, you will have neither. If it's positive to positive, you'll have something that looks like an x cubed, and negative to negative, you'll have something that looks like a negative x cubed. So no local extrema in those cases. So I'll look at a couple examples using the first derivative test to find the increase and decrease intervals and the maxes and mins. So we'll start out, we'll take the derivative, which in this case will give us 15x to the fourth minus 15x squared. This derivative exists everywhere because it's a polynomial, so we don't get any critical numbers from the derivative not existing, so we'll just set the derivative equal to 0. As I do that, I'll pull out a 15x squared, leaving me with x squared minus 1 in parentheses. That means we'll have 15x squared, and this will factor into x plus 1 and x minus 1. And when you set them each equal to 0, we'll get that x is equal to 0, technically plus and minus 0, but it's the same thing. X equals negative 1, and x equals positive 1. These are the values that we'll put on our number line. Remember, when you test on your number line, you're plugging into the derivative, and it's usually easiest to plug in the factored form. Test a number like, say, negative 2. Well, we'll get back a negative, a negative, and a negative. A negative times a negative times a negative. Or sorry, the first one will be positive because it's squared. So you'll have a positive times a negative to give you a positive. The next section, test like negative 0.5. You'll again get the positive back because of the squared, another positive back, and a negative. So that section will be negative. In the next gap, test a positive 0.5. The squared will give you positive. The next section will be positive, and then we'll still have another negative. So that stays as a minus. And then test something like 2. You'll get positive, positive, positive to give you a plus. So first, our intervals of increase, decrease. We are increasing from negative infinity to negative 2. And then the union of that with, or sorry, not negative 2. Negative 2 is our test number. Negative 1 would be our interval value. And the union of that with 1 to infinity. We are decreasing from negative 1 to 0, and then again from 0 to positive 1. We can't include the 0 because at 0 we have a horizontal tangent line there. We are neither increasing nor decreasing. And now for our local maxes and mins. Well, in this first section, we're going from increase to decrease, which will create a maximum. So at negative 1, we'll have a max. At 0, we're decreasing, then decreasing again, so we have nothing. And at 1, we're decrease to increase, so we'll have a min. So that'll be at 1. Now, because the max and min are values in your actual function. You have to plug them into the original. When you plug in -1, you'll get back a -3. And then -5 times the -1 to give you a +5, so you'll get back +2. When you plug in +1, you'll have 3 minus 5, so you'll get back -2. We'll do the same idea with example 2. We'll start out taking the derivative. 3x squared minus 6x. We'll set that derivative equal to 0, and as I do that, I'm going to pull out a 3x. We'll set each part equal to 0, giving us the x equals 0 and x equals 2. Those are the values that we will put on our number line. Remember to test in your derivative in the factored form. We'll test something like -1. When we do that, we'll get a negative times a negative, which is a positive. In here, we can test something like +1. We'll get back a positive times a negative, which is a negative. And in here, we can test something like 3. We'll get a positive times a positive, which is a positive. So we're ready to do our increase-decrease intervals. We'll be increasing from -infinity to 0, the union of that with 2 to infinity. And we'll be decreasing from 0 to 2. Now when you go increase to decrease, that'll give you a max. And that's occurring at 0. And when you decrease to increase, that'll give you a min. And that's occurring at 2. Keep in mind, when you find your maxes and mins, those are y values in the original function, so you need to plug it back into f. When we plug 0 in, everything wipes out except for the 5. When we plug 2 in, we'll get 8 minus 12 plus 5, giving us a +1 for the local min. Now one last first derivative test example. We'll take the derivative. And we'll set that derivative equal to 0. As we set it equal to 0, I'm going to divide everything by 3. The reason we can divide by 3, there's no x's when you divide by 3. You can never divide by a variable, but you can divide by a constant. So we end up with x squared minus 2x plus 1, which factors into x minus 1 times x minus 1. When we set those equal to 0, we just get x equals 1 twice. So that's the only value for our number line. Again, in all of these ones we've seen on this page, the derivative exists everywhere because they're polynomials, so we don't have to worry about any critical numbers where the derivative doesn't exist. We always test in our number line in the derivative, and the factored form is usually easiest to test. So we can test something like 0 here, where we'll get back a negative times a negative, which will end up giving us a positive. Over here, we can test something like 2, which will give us a positive times a positive, which will give us a positive. We are only increasing here, and we're increasing from -infinity to 1, and then again from 1 to infinity. We need to exclude the 1 because at 1 we have a horizontal tangent line. We are neither increasing nor decreasing. And because we're going increase to increase, there are no maxes or mins. So we can just state that. And we will have now satisfied the question, finding our increase-decrease intervals and where any maxes or mins might occur. So hopefully after this video, you're solid now with Rolle's theorem, mean value theorem, and the first derivative test. That's all for today's video. We'll see you next class, period.